When you think about any truly great sporting moment, that perfect three-pointer, a record-shattering long jump, or a free kick that just seems to bend impossibly, it really feels like magic, doesn't it? But here's the thing. Every single one of those moments is actually governed by the unshakable laws of physics. Today, we're going to pull back the curtain and unpack the science of projectile motion and see how the world's best athletes learn to bend it to their will.
Okay, so let's get right into it. The instant an athlete leaves the ground, whether it's a high jumper, a gymnast, or even a sprinter in mid-stride, their body is, for all intents and purposes, a projectile. They're basically subject to the exact same forces as a cannonball or a javelin.
And that, of course, leads us to the big question we're going to tackle. What are the scientific principles that actually dictate that arc through the air? How on earth do athletes manage to control what seems like a completely uncontrollable flight path?
To really get our heads around the complex reality, we've got to start simple. Let's strip it all back and imagine a perfect world. A world where the only thing that matters is the constant, steady pull of gravity. First things first, just a quick definition so we're all on the same page. A projectile is basically any object that's moving through the air, where for our simple model right now, we're only going to think about gravity's influence. Now, in the real world, air resistance is always there, but don't worry, we'll get to that in a bit.
Right, so in this perfect vacuum-like world, the path of any projectile is this beautiful, predictable, symmetrical arc, a parabola. The moment it's launched, its fate is sealed. Its entire trajectory is completely set.
So here's the crucial part. While the flight path itself is out of their hands once they're airborne, athletes have three really powerful levers they can pull right at that moment of release to control the path: how fast they launch it, the angle they launch it at, and the height they launch it from. And, tweaking each of these initial conditions has a direct result on the outcome. It's cause and effect. A higher initial speed means more range. Simple as that. Changing the angle? Well, that affects both how high it goes and how far it travels. And of course, a higher release point just gives the projectile more time in the air to go farther.
But of course, athletes don't compete in a vacuum, do they? So let's move on and see how the real world fights back with a force we're all familiar with: air resistance, or as it's known in physics, drag.
See? In that perfect world model we just talked about, an object's forward speed would never, ever change. It would just keep coasting along horizontally while gravity does its thing and pulls it down. But that's not what really happens, is it?
The reason it doesn't happen is because of the drag force. The easiest way to think about it is like friction, but with the air. As an object tries to shove air molecules out of its way, those molecules push right back, and that slows the object down.
Now here's where it gets really interesting. The importance of drag completely changes depending on speed. For something slow-moving, like a heavy shot put, gravity is still the king. The arc is pretty close to that perfect parabola. But for fast-moving objects, whoa, drag becomes a huge deal. It cuts the flight short and makes that downward path way, way steeper than the upward one. It becomes asymmetrical.
And if you want a really dramatic example of this, just look at badminton. The fastest recorded speed of a shuttlecock is an absolutely mind-blowing 117 meters per second. That's over 420 kilometers an hour. At that insane velocity, that incredibly light little shuttlecock just gets slammed by air resistance. It leaves the racket like a bullet, but then it slows down so incredibly fast that its flight path becomes super lopsided. It's maybe the perfect real-world example of drag in action.
But here's the thing about elite athletes. They don't just fight against these forces. No, the best of the best actually learn how to harness them. They use the air itself to create spin, lift, and swerve.
So how do they do it? Well, the key to understanding all this is a concept called Bernoulli's principle. It's actually pretty simple, but it's incredibly powerful. It just says that wherever air moves faster, it creates an area of lower pressure. Just remember that. Faster air equals lower pressure.
And it's this pressure difference that generates what we call a lift force. And what's so critical to understand is that lift doesn't push backwards like drag does. It pushes at a right angle to the object's motion. This is exactly how an airplane wing works, and it's how athletes can make a discus or a javelin seem to just hang in the air for that extra split second. Now, when you take this idea and apply it to a spinning ball, you get something called the Magnus force. The spin literally drags air around one side of the ball, making the air move faster on that side. And what did we just learn? Faster air means lower pressure. So the ball gets pushed or swerves right in that direction. This is the hidden physics behind every curving free kick in soccer or every nasty breaking ball in baseball. So when you start to put all of this together, you've got gravity, you've got drag, you've got lift, and those three initial launch conditions, you start to realize that elite athletes are basically intuitive physicists. They are performing these incredibly complex calculations in their heads to master the perfect angles for their sport.
Now, remember how in a perfect world, the best angle for maximum distance is always 45 degrees? Well, take a look at this data. Almost nobody actually uses 45 degrees. Long jumpers are way below it. Basketball players are way above it. And golfers, they're at a super low 10 to 20 degrees, so what in the world is going on here?
Okay, let's break it down. For a long jumper, it's a trade-off between angle and speed. Their leg muscles just can't generate maximum power at that steep 45-degree angle. A shot putter is already releasing from way up high, so a slightly lower angle is just more efficient. A basketball player, well, they have to get the ball up and over to get to the hoop, so they need a much higher angle. And a golfer, they are masters of the Magnus effect, creating backspin to generate lift, which literally keeps the ball in the air longer, even with that really low launch angle.
And here it is, maybe one of the most fundamental rules of all of this. Once an athlete is airborne, the path of their center of mass is locked in. It's set in stone. No amount of flailing their arms or kicking their legs can change that predetermined arc. All those incredible movements you see in midair, that's all about positioning their body parts around that unchangeable center of mass, either to clear a bar or stick a perfect landing.
Which kind of brings us to a final thought for you to chew on. We understand this science better than we ever have before. We can design shoes, rackets, balls, and techniques to manipulate these forces almost perfectly. So the real question becomes, as we continue to master the physics of sport, where do we draw the line between celebrating pure, raw human achievement and gaining an unfair technological advantage? Something to think about.